Okay, so we're focusing on I squared and what that means. But before we do that, I'm going to build up to it and first ask the question, what does square root of 16 mean here? What does that mean? Not what's the answer. You can tell me the answer, but what is it asking? Or what is it wanting us to think about? Well, it's asking, excuse me, it's asking what number or numbers can be multiplied by itself to equal 16. And then the answer here is positive and negative 4. So the square root of 16 is positive and negative 4 because positive 4 times positive 4 is 16 and negative 4 times negative 4 is 16. The next question here is what does this square root of 3 squared mean? Well, the square root of 3 says, well, what number or numbers can be multiplied by itself to equal 3? And then we're going to take that result and square it. So I'm going to copy all of this because I'm lazy, right? Mathematicians are kind of like that. I don't think it's going to let me. My app is not letting me copy this morning. Oh, there we go. Didn't want to let me be lazy. And so what number or numbers can be multiplied by itself to equal 3? And then we're going to take that number and or numbers and multiply by itself. And it turns out that the answer is 3. Questions on that idea? So then the thing that we're really getting at here is what does I squared mean? Well, remember that I is equal to square root negative 1. So I squared is equal to square root negative 1 squared. Well, when we look up here, we had square root of 3 squared, and here we have square root negative 1 squared. So what should the answer be for square root of negative 1? It's kind of unintuitive, maybe. It's negative 1. So check that out. We're squaring a number, and the result is negative. That's because we're squaring a complex number. I is a complex number. That's the only way when you square something that you can get a negative. All other times, whenever we multiply a number by itself, those real numbers, we always get a positive. But with complex numbers, we can get negatives. So that's really important. Anyone want to ask a question about that before we move on? All right. So now I want you to notice a connection. So we're focusing on I here today, complex numbers, but looking at these binomials that we're adding together, and look at how they are similar to these two complex numbers that we are adding together. Wow, they look so much alike. And the math, the way we do the math, is so similar. So we have 3 plus 2 and x plus 7x. And we saw before that that was 5 plus 8x. And in these complex numbers, 3 plus 2 and positive I plus 7i is going to be 5 plus 8i. The math itself is the same. Okay? Similarly, 7 plus 5x minus the quantity 2 plus 3x. We're going to do that the same way as well. 7 minus 2 is 5. 5x minus a positive 3x is plus 2x. 7 plus 5i minus the quantity 2 plus 3i. Well, 7 minus 2 is 5. Positive 5i minus positive 3i is plus 2i. Really, really similar. Hope you guys see that connection there. Here, in the next ones, we have a number times a binomial. So 2 times 3 and 2 times x. 2 times 3, that's 6. 2 times positive x, that's plus 2x. In this one, we have the number 2 times a complex number. We have to distribute the 2. 2 times 3, that's 6. 2 times a positive I is plus 2I. And on the last examples here, we have two binomials that we are multiplying together. Here we have two complex numbers that we're multiplying together. And the process is going to look really similar. We're going to use FOIL in both cases. 2 times positive 1 is 2. 2 times positive 3x is positive 6x. X times 1 is x. X times positive 3x is plus 3x squared. Now we can combine those terms, and I know I'm doing these for the second time. These were the warm-ups as well. But I just want to make really clear the connection between these two examples. Now the next one, the first step is going to be the same, but then it's going to get a little bit different. Okay? I'm going to use a different size pen here because I'm going to need a little more space. So 2 times 1, that's 2. 2 times 3i is plus 6i. I times 1, that's I. And I times 3i is plus 3i squared. So far, that's really pretty much the same. It's just instead of the unknown value x, we have the I. Now, I can combine my I terms. So I have 2 plus 7i. And this I squared, remember, we just talked about I squared equals negative 1. So we have plus 3 times negative 1. Now this is going to be negative 3. When we combine negative 3 with a positive 2, we get negative 1 plus 7i. So these steps are just a little different than over here, but hopefully you don't find them to be too confusing. Are there any questions at this point? All right, we're going to pause right here and have a quick move break. If you're watching this video, probably a good idea to get up and move your body. Okay, now we're going to talk about how to represent these complex operations on a grid. And notice that the grid, this is a complex grid because we do have our x-axis here, but up here we do not have a y-axis, we have an I-axis. So the grid works the same way that a grid would normally work with xy's, but with xi's. So I'll show you how it works here. We're going to look at this 3 plus I. So you can kind of think of that like a coordinate point if the coordinate point were 3i. That's kind of the way to think about it. So the 3 plus I is right there. That's where it is. And when we think of these, complex numbers on a grid, we think of them like a ray. And I want you to think about a ray the way you think in physics. It has direction and length. The way in physics you have direction and force when you're talking about what is it that I'm thinking of? Direction and force, that is, someone help me out here. Come on. No? Okay. We'll just have to leave it. All right. So there is my 3 plus I. And here is my 2 plus 7i. So 2 plus 7i right there. And this is going to go up like that. Okay, so what we do now is we take each ray and we do the same thing from the other ray. And here's what I mean. This ray goes to the right 3 and up 1. So from this ray, we go to the right 3 and up 1, and we're going to make a new ray right there that is a copy. This ray is a copy of that ray. And we're going to do the same thing from this ray. We're going to take this ray and we're going to copy it. And I'm literally going to use the copy feature here. And I'm going to paste it just so you can see what happens. Is it points to that same spot right here, this same point. And if we look at that point, we can see that it is 5. So it's 5 plus 8i. So this point right here also has a ray. And that new ray is the ray 5 plus 8i, which notice 3 plus 2, that's 5. I plus 7i, that's 8i. So this ray that is the result of adding those two rays together. And we can do it this way, And we can do it this way, which means basically it doesn't matter which order we add in. And this is the resultant ray from the addition. Resultant, result. It's the result of addition. All right? And there's no reason why it's a dotted ray. It can be a solid ray there. And you may wonder, why do we care about putting these things on the graph? It's so easy to add them like this. It is easy. I hope you think so. If you're having some trouble with it, please ask questions and come see me during the async as well. But it's going to be pretty cool to see what we can do with this kind of graphing, especially in quadratics. We're not going to be focusing on it this semester, but we'll get into it later. And it also connects up with trigonometry really nicely. It's like a three-dimensional grid where you have your x's, your y's, and then this way is your i's. And so it's like a cube with x, y, and I in the directions. All right. So 7 plus, I'm going to actually copy this. Did I do it here? Yeah. So we have the 7 plus 5i and the 2 plus 3i. Notice that here we're subtracting. So the 7 plus 5i, it's right, whoops, I want blue. It's right there. And now because we're subtracting, we can distribute that subtraction and turn it into addition. So that's what I'm going to do. We have the 7 plus 5i, and I'm going to distribute. I'm going to put that in parentheses just to keep it separate. I'm going to distribute that subtraction so it's -2 minus 3i, and then the subtraction becomes addition because what we did is we distributed it in like that. And now this is what we can graph. So -2 minus 3i is right there. Okay, so what I can do is I can take this and I can copy it and paste it over here to the end of the blue one. And then I can take the blue one here, copy it, and paste it over here to the end of the red one. And then what happens, just like what should happen, is we have this point right here that creates a ray. And that ray is the result of the subtraction, and it is 5 plus 2i. Questions on that one? So notice that we've created this parallelogram right here in the subtraction and in the addition. The multiplication is a little different. So we're going to start with the 3 plus I and graph that. And then what we do, because we're multiplying it by 2, is we stretch it. And we stretch it by a factor of 2. So I'm going to see if this is going to work. Let me see. I'm going to copy this, and I'm going to paste it. And I'm going to put it right here. I'm going to change the color on it to a red so that you can see it separately. And then I'm going to stretch it I can't stretch it in place very well because of the way that the stretch works on this, but trying. There we go. So you can see that when I stretch it by a factor of 2, I get this point right there, which is the result of distributing the 2. I get 6 plus 2i. And this point right here is the point 6 plus 2i. Now, when we multiply like this down here, it turns into a rotation. And it's rotating around. It's pretty cool, but we're not going to do that today. Questions on the multiplication? Multiplying a complex number by a constant. So multiplying a complex number by a constant. All right. Here this is going to be an introduction to where we're going. You did this in Algebra 3-4 last year, and you probably, you maybe don't remember it. And that's okay. We will work through it together. So we're given these 2 roots. Those are roots to the equation, and you can think of those like x-intercepts on the graph. So the point 10 would be an x-intercept, and the point -60 would be an x-intercept. And we also have this other point that is on the graph. And this wants us to find the equation of that quadratic function. So we're going to use the x-intercept form of a quadratic equation. And remember that what that is f of x is equal to a times the quantity x minus p times the quantity x minus q, where p and q are the roots. So we need to solve for a, and we're going to plug in 1 for p, that's one of our roots, -6 for q, that's our other root. All right, we're also going to use our x value here and plug it in for x. And then we will plug in the y value here for y. And that will allow us to, in turn, solve for a, which is really the goal here. All right? So we have -36 is equal to a times the quantity. X is -2 minus p is 1. And I usually put that in parentheses, and you'll see why in just a moment. And then our x value again is -2 minus, and here the q value is going to be -6. Whoops. Need red there. -6. And this is why I put it in parentheses, because when I plug it in, the -2 minus 6 would look weird if it were -2 minus a -6. That just is kind of bad representation. So having it in parentheses is a good idea. All right. So we have -36 is equal to a times the quantity. -2 minus 1, that's -3. -2 plus 6 is +4. We can see that this is -12 times a. So I'm going to divide by -12, and I get 3 is equal to a. So now my equation then is going to be f of x is equal to, my a value is 3 times the quantity x minus my p value, remember, is 1 times the quantity x minus my q value is -6. So I'm just going to change this to a +6. Questions up to that point? There's a little bit left to do, but I don't want to move on before everyone feels good with what we've done. Annika, thank you for the feedback. Sometimes it is a little like teaching into the void. So, oh, by the way, the artwork's nice today, huh? I like it. Yeah, there you go. They didn't, the artist did not ask me to share their name, so I will not. So this is a perfectly good function written in x-intercept form. But if we want to write it in standard form, then we need to do a little bit of work. So we have f of x is equal to 3, and then we're going to do FOIL on this. We're going to FOIL that out. X times x, that's the first is x squared. So x times x is x squared. Outers, x times +6 is +6x. Inners, -1 times x is -x. And lasts, -1 times +6 is -6. Combining those terms inside the parentheses, we have 3 times the quantity x squared plus 5x minus 6. Distributing the 3, we have f of x is equal to 3x squared plus 15x minus 18. And there we have our quadratic function written in standard form. All right? It's a little bit of work. How many of you guys remember doing that last year? Give me a thumbs up if you remember doing that. Annika does. Good. Tommy does. Excellent. Josh, Shet, Anna, Holly. Sweet. So that's good news. Some of this stuff stuck. You should go back and thank your teacher. They did a good job. So, this, however, is when our x-intercepts are real. We have real number x-intercepts. When our roots are complex, we don't have x-intercepts, but we can still find the equation. This seems like it's going to be hard. Let's take a break and get some blood flowing to our brains. And I see 2 folks added their cameras here. Thank you so much. I appreciate it. When we come back, please keep them on. It's great. I love it. Is everyone ready for something tough? No, not everyone. All right. I'm going to be right there with you, though, I promise. We're going to do the same basic thing we did over here. Okay? We're going to take our roots and we're going to plug them into P and Q. Our y value, plug it in for, or our coordinate, plug it in for x and y, and then solve for a. All right? So here, our roots are 3 plus 2i and 3 minus 2i. Our x value is 2, and our y value is 10. So we're going to start again with f of x is equal to A times the quantity x minus p times the quantity x minus q. And we're going to plug in our 3 plus 2i right here, our 3 minus 2i right here. We're going to plug in our x value here and here. We're going to plug our y value in there and then solve for a. Notice that because we've plugged something in everywhere except for a, we'll be able to solve for a. That's why this works. Math can be such a thing of beauty when we just let it. It's so good. All right. So our y value is 10 is equal to a times the quantity. X is 2 minus p is 3 plus 2i times the quantity. X again is 2 minus 3 minus 2i. And there it is. Now, for the first, so notice that we have two things that are really similar right here, and we're multiplying them together. It's this last step where we multiply those together, where we have to do a FOIL inside of a FOIL. So has anyone ever seen, shoot, what's it called? Where they go dreams inside of dreams and they plant an idea. It's conception. Thank you, James. So it's like Inception. Thank you, James, for the correction as well. Inception, great movie. I loved it. In fact, just watched it recently again. And this, a foil inside of a foil, is just like Inception, which probably won Academy Awards. So this should probably win Academy Awards too, if you follow my logic. All right, so let's do it. So we have the 10 is equal to the a, and we have to multiply the a times the result of multiplying all of this. So we need parentheses with the result of the FOIL inside it, and it's actually going to be more like that. Okay, so firsts, 2 times 2, that's 4. Ooh, I like that start. That's a nice easy start. Outers, ooh, here's a little bit more difficult. So 2 times negative 3 is negative 6. And then 2 times positive 2i. Oh, you know what? Let me do this instead. I'm going to try to make it a little more clear here this first time. So again, I'm going to multiply 2 times all of that. See if I can make it nice and clear here. So what I did is I multiplied the 2 times all of this, but I distributed that negative, and that's why those signs switched. Is that okay? Because that's the outers. So now I'm going to do inners. So I'm going to multiply this times that 2. Okay, but I'm going to distribute that negative. So it's going to be plus negative 3 minus 2i times that positive 2. So again, I just did inners, this times that. And now my lasts are going to be this times that, and that's where we're going to end up having to do a FOIL inside a FOIL. All right, so that's going to be plus. And again, I have to distribute the negative here. So I get negative 3 minus 2i. And I have to distribute this negative. So I'm going to get negative 3 plus 2i. And so this parentheses and that parentheses match up. So we're multiplying all of this times a. Is it good? It's a lot. Step by step, though, can you follow what I did? Anyone have a question right here before we do the next steps? All right. 10 is equal to a times the quantity 4. Now we're going to distribute the 2 and get negative 6 plus 4i. Now here, we're going to distribute that 2 and get negative 6 minus 4i. And now we're going to FOIL here. Okay? So, negative 3 times negative 3 is positive 9. That's first. Outers. Negative 3 times positive 2i is negative 6i. Inners. Negative 2i times negative 3 is positive 6i. And negative 2i times positive 2i is negative 4i squared. Now, does anyone see something nice? What's nice in here? There really is something nice. What happens with those? They cancel. What happens with these? Those cancel. And we remember that I squared is a negative 1. So we're not going to have any i's left after this, which is great. So we have 10 is equal to a times the quantity. 4 minus 6, then these i's cancel. So we have minus 6 there again, plus 9. Those negative and positive 6 i's cancel. And then it's minus 4 times negative 1. So far, so good? It's not easy. It's just a lot of steps, right? I mean, the math itself you've done, but it's just the number of steps it's hard to keep track. So now we have 10 is equal to a times, actually, let's just do the order differently here. So this is going to be 4 minus 6. That's negative 2. Negative 2 minus 6 is negative 8. So here we have negative 8. Negative 8 plus 9. Negative 8 plus 9, that's 1. So this is all 1. And then negative 4 times negative 1 is positive 4. So we have 1 plus 4 is 5. So this is 5a. Dividing by 5, a is equal to 2. So our function f of x is equal to a is 2 times the quantity x minus, and then again we have to go back to our complex numbers. 3 plus 2i times the quantity x minus 3 minus 2i. Now, I'm going to copy that because we're not done. Just like we weren't done before, we're not done now. All right? I'm going to bring it over here. So now we have to rewrite this in standard form, because you'll see something nice happens when we write it in standard form. All right, so we have f of x is equal to 2 times the quantity. X times x, that's x squared. X times negative 3 is negative 3x. And x times positive 2i is 2xi. Inners, so we're multiplying this times x. So x times negative 3 is negative 3x. X times a negative 2i is negative 2xi. So all we have left are last, and we do recognize, again, that's a FOIL inside a FOIL, so it's kind of a pain in the butt. Negative 3 times negative 3 is positive 9. Negative 3 times a positive 2i is negative 6i. Inners, negative 2i times the negative 3 is a positive 6i. Did I mess up somewhere? I think I did. This, the 9, this should have been minus 6xi. Sorry. And then this, again, negative 2i times negative 3. Where did this x come from? I am making stuff up. I'm sorry. Positive 6i. Again, let me try that again. So this negative 2i times negative 3 is going to be a positive 6i. I knew that it couldn't be right because these weren't canceling, and they have to cancel. And lastly, negative 2i times a positive 2i, because of these out here, is going to be a negative 4i squared. And, great. Jeez, it's so much. Yeah, it is. But we have the x squared, and then we have a negative 3x and a negative 3x, and that's a negative 6x. Positive 2xi minus 2xi, those cancel. Plus 9 right here. Negative 6i plus 6i, those cancel. Negative 4 times negative 1. Distributing the 2x squared. 2 times negative 6x is negative 12x. Combining these two, we have 9 plus 4 is 13. 13 times 2 is 26. And look at that. We have a normal quadratic. That's just a parabola. And the interesting thing about that parabola is there are no x-intercepts. If we did the quadratic formula on it, this is what we would get. That would be the result of the quadratic formula. So we've done like the reverse of the quadratic formula. Questions here? Is it hard? Yes. A lot of steps.